Hello everyone. In this video, we are going to design a dog-legged staircase. Another example, in the earlier video, we had designed the dog-legged staircase. So in this video also, we will try to design a dog-legged staircase of having a stair hall of size 4.75 meters by 3.1 meters. We are going to have a riser and tread uh, of step as 150 mm and 250 mm respectively. Width of the stair is 1.5 meters. Live load as 5 kilonewton per meter square. Flow finish as 0.75 kilonewton per meter square. We have to use M20 grade of concrete and Fe415 steel. So after the end of this design, we will try to do the detailing of this staircase. So let us try to see. So if you compare it with the previous problem, so this was the staircase. In the previous problem, if you see the staircase, it was supported by the beams or walls on the end of the landing. So here it was supported. But in this case, what happens is that if you see it is supported, this landing support, it is supported in this direction. So landing is supported by a wall or beam in this direction. So now how to calculate the effective span? So there we'll have the variation, other things will remain same. So that is the difference between the previous problem and this problem. So now let us try to see what this figure shows. So we are going to have a landing width of 1.25 meters and going of 3.3 meters, again 1.25 meters we have. Similarly here 230 mm thick wall we have 1.25 meter, next 1.25 meter, 3 meter, total width is 2.8 meters. So this much data we have now. So only the variation will be how to calculate the effective span. So effective span will be center from this till this. So there are certain clause which is being given in the IS 456, that also we will try to see, right? So riser is 150 mm, tread is 300 mm, FCK is 20, F of Y is 415, live load is 3, flow finish is 0.6. Then next is how to calculate the effective span. So if you refer the code book, in the code book you can see in the page number 63 they have given it for stairs, that is effective span of stairs. Effective span of stairs without stringer beams shall be calculated somewhere here. So when supported at the top and bottom riser by beams spanning parallel to the riser, that was the previous problem what we had solved. So therefore the effective span what we had taken was center to center of the beams. So for example, here we have one beam and here we have one beam. So distance, that center to center distance of the beam will be the effective span. Then next is second case is where spanning on the onto the edge of a landing slab which spans parallel with the riser, right? So a distance equal to the going plus at each end either half the width of the landing or 1 meter. Half the width of the landing or 1 meter. That means we have to take this going plus here what landing we have, half the width of the landing or 1 meter, whichever is what you can say, half the width of the landing or 1 meter, whichever is smaller, right? So if it is greater than 1 meter means we have to take it as 1 meter. If it is less than that, we can have the value, right? So for that you can see here, now this is the table what they have given. This is X landing slab we have, Y we have here. So how to calculate the effective span? If it is less, X is less than 1 meter, then we are going to use it as going plus X plus Y. If both the things are less than 1 meter, we'll take going plus X plus Y. So if X is less than 1 meter, Y is greater than 1 meter. When Y is greater than 1 meter, instead of taking this Y, we will take it as 1. So if you see here, X is greater than 1, right? So instead of X we will take 1, Y will be as it is, going plus Y. If both the things, if they are greater than 1, if this is also greater than 1 and if this is also greater than 1, then we are going to use going plus 1 plus 1 meters, right? So here let us try to see now. So we'll try to calculate the landing slab width is 1.25 meters. So here if you see, we have to take half of that, 1.25 divided by 2. So this is 0.625. So as this is less than 1, we can consider this value. So similarly, y also will be 0.625. This is also less than 1. So therefore, we can consider this. That is going plus x plus y we can have. So if you see, this condition applies to our span now. Both the x and y, they are less than 1. So therefore, effective span will be g plus x plus y. That is g plus x plus y. So that will be the effective span. Therefore, 0.625 is x, g is 3.3, y is 0.625. So effective span will be 4.55 meters. Then next is waste slab thickness. We will assume 50 mm per meter length. So therefore depth will be 50 multiplied by effective span is 4.55. We will get 228 mm, or we can assume overall depth as 230 mm and effective depth as 200 mm. Next is load per meter width. What is going to come, we'll try to calculate. First one is self weight of the waste slab. So already we know this formula, d into square root of t square plus r square divided by t multiplied by 25. D is nothing but the depth of the waste slab, that is 230 mm. T is nothing but tread, zero point 0.3 we have. Riser is 150 mm divided by 0.3 multiplied by 25, that will be equal to 6.45 kilonewton per meter. Then next is we'll try to calculate the weight of these steps, that is half into r into t divided by t multiplied by 25. So if you substitute riser and tread value, you'll get answer as 1.875 kilonewton per meter. Then next is we have live load, that is 3 kilonewton per meter. We have flow finish, that is 0.6 kilonewton per meter. So if we are going to add up total load, it will be 11.9 kilonewton per meter. So for factored load, we will multiply it by 1.5, that will be 17.85 kilonewton per meters. Then next is load on the landing per meter width. We'll try to calculate. So self weight of the slab, that is thickness multiplied by density, that is 5.75. Now per meter width we are calculating, so multiplied by 1. Flow finish 0.6 kilonewton per meter. Live load, it is 3, so total load will be 9.35. So factored load will be 1.5 multiplied by 9.35, that is 14 kilonewton per meters. So based on that loading, you can see 14 is the load on the landing. So this is the landing now, on that it is 14. Then next is on the waste slab, what you can say, on this going we have 17.85. So we have 17.85 somewhere from this point till this point. Again this is landing, it is 14 kilonewton per meter. So based on this loading, we have to calculate the bending moment and shear force. So already in the previous problem also we had calculated the bending moment and shear force. On same guidelines we can calculate the bending moment and shear force. So first what we have to do, as the loading is symmetric, we have to calculate the reaction at A and B. So total load divided by 2 we can have. Total load will be equal to 14 multiplied by 0.625 plus 17.85 multiplied by 3.3 plus 14 multiplied by 0.625. That will be the total load divided by 2. We will get reaction at RA and we will get reaction at RB. Then next is we have to calculate the bending moment at the center. So RA into this distance, that is 0.625 plus 3.3 divided by 2. Then next is movement due to this 14 kilonewton meter. It is going to cause anti-clockwise movement. So therefore 14 multiplied by 0.625, this will be the total load multiplied by distance. Distance will be 0.625 divided by 2 plus 3.3 divided by 2. That will be the distance. Then next is loading due moment due to this 17.85 kilonewton meter. This is anti-clockwise. So therefore 17.85 multiplied by 3.3 divided by 2. That will be the total load. Now distance will be 3.3 divided by 4. So if you do that, you will get the bending moment, that is 43 kilonewton meters. So shear force will be 38.2 kilonewton meter. So in the earlier problem, what all things we have checked, everything will remain same. We have to check for limiting moment. Then next is D required. Then next, based on that, we have to calculate the area of steel, that is 638 mm square. So if you provide 10 mm bars, we can have it at 120 mm center to center. So percentage of steel provided will be 0.327 percentage. Next, distribution steel, we can provide 0.12 percentage of gross area. So based on that, requirement is 276 mm square. So we can provide 8 mm dia about 170 mm center to center. Then next is for design for the landing slab. Again, effective span will be 2.8 meters plus thickness of the wall divided by 2, that is 230 by 2, 230 by 2. So effective span will be 3.3 for the landing slab. So load on the landing already we had calculated 14. So bending moment of on that landing will be WL square by 8, that is 16.06. So for that, if you calculate, area required will be 238 mm square, which is less than distribution steel. So therefore we can provide the 8 mm bars at 170 mm center to center. Then next we have to check for shear and we have to check for deflection. So you can stop and you can refer this and you can make a note of this. Check for shear and check for deflection. And at the end we have to do the detailing of the reinforcement. So what happens is that main reinforcement already always it will be provided at the bottom. Here you can see this is the reinforcement what we provide, main reinforcement, and the circles what we have, this will be the distribution steel. So from top also you can have it here, and from here bottom you can take it to the top and you can provide it here. So in this way detailing has to be done. You have to take this as the main bar and this has circles as the distribution bar. Then next is another question is it is same as that, just simply I'll tell you what is the difference in this problem now. So here what happens is that they have said us to calculate only for a single flight stair. They have said us to do the calculation. Number of steps is 12, tread is 300, riser, width of landing beam is 400 mm. So we have to do the detailing again, same thing. So here effective span will be total going plus the width what we have 400 mm. So therefore it will be 4 meters. So again same thing, we will calculate the waist slab, that is 50 mm per meter width. Then next is we'll try to calculate the load on the waist loads of the waist slab, that is self weight, weight of the steps. Then next is live load, floor finishing, we'll have total load, dead load as well as live load. So if you do it factored, we'll be getting answer as 19.9 kilonewton meter. So based on that, we'll have the loading. So here in this case we don't have landing, so only we have going, that is total load is 19.9. So therefore based on that, we'll try to calculate the moment, as like loading was in the previous problem loading was varying. So here it was less and here it was more, but here in this case we don't have, only one single going we have. So therefore due to that very easily we can calculate, as it is a UDL WL square by 8, and we can calculate the shear force. Based on that moment and shear force, we'll try to calculate the reinforcement based on that. So area required will be 711 mm square. So based on that, if you provide 12 mm bar, you require 158 mm. So we can provide 12 mm dia bars about 150 mm center to center. And if you calculate the distribution steel, it will be 240 mm square. So if you are going to use 8 mm bars, requirement will be 208 mm. Right? So everything will remain same what we had solved in the previous or earlier problem. So same concept has to be applied. Only slight variations we have. Right? So here if you see now, this is how the detailing has to be done. In the previous problem we had a landing, then next flight we used to have it in this way, but here in this case we don't have landing. So from the beam itself our reinforcement is starting. So therefore now, so in this way the detailing has to be done. Main reinforcement and distribution steel. Main reinforcement is 12 mm dia about 150 mm center to center, and the circle what we have is 8 mm dia about 200 mm center to center. So here at the end we have the beam at the start and end of the going. So this as a assignment you can solve it.